Hi everyone, in this video we are going to discuss Lewis symbols, but in order to do that properly we absolutely need to review valence electrons. So for valence electrons, if you recall, they are your outermost electrons. So if I were to draw out an atom, I would have to start with a nucleus. So the nucleus is at the very, very center. That's where your protons and your neutrons are stored. It is tiny. It is minuscule. It's very, very small. So what's cool about an atom is its very first shell, so the first one that's right around the nucleus, that one has 2 electrons in it. So we'll just put one here and one here. But because the nucleus is so small, that first shell is also just so tiny that it can be very tightly compact around the nucleus. It's so small that it can actually only hold 2 electrons. Because from there on out, every single other shell around it wants to have 8 electrons in it. And so it will just keep growing and growing, and every single shell will have 8 electrons. So now, if you recall, we're talking about this in the context of valence electrons. So for my example here, I have a nucleus in the center, and I have 1, 2, 3 shells on around it. So these first 2, this one and this one, these are considered your core shells. They house your core electrons, so they hold them very tight to your nucleus. But on the outside here, we have our outermost shell, and this is the one that houses our valence electrons. So when we go to a periodic table and try to determine the number of valence electrons, we're actually talking about the electrons that are sitting in the outermost shell. So now what's really neat about this is because we have an inner shell that's so small and only houses 2 electrons, we actually have to kind of manipulate the periodic table when we're determining valence electrons on our own accord. So what we're going to do here is look at our periodic table and specifically look at this very first row. So we said it can only have 2 electrons in its outermost shell. And so what we need to do is just come over here and we're going to actually move helium. So I'm going to put it right here above this second group, and we're going to cross out helium over here. So now what I'm going to do is go, starting from the left, we're going to go across and number our valence electrons. So for this first group, our alkali metals, they only have 1 valence electron, just 1. So if we were to draw it out in our diagram, here is our nucleus, there's our shell, they have just 1 electron sitting in the outermost. Then we go to the second group, or our alkali earth metals. They have 2 valence electrons, so 1 and 2, and so on and so forth. So we go to boron, which has 3, then 4, 5, 6, 7, and 8. Hopefully this is all a review, but we need to understand that in order to actually draw our Lewis symbols. So let's start off with hydrogen. Hydrogen has the symbol H, and we know, because we just discussed it, that hydrogen has 1 valence electron. It's sitting here in the first group, so I'm going to come down here and just draw it out. So this is a Lewis symbol for hydrogen. I'm saying that it has 1 valence electron. So let's say I go down in the alkali metals and go to lithium. Here's lithium. It also has just 1 valence electron, so I would draw it in the same manner as hydrogen. We can go on and on and on with sodium and potassium and rubidium, but essentially you just draw 1 electron to the side of it. So let's move on to the second group, our alkali earth metals. So let's start with helium here. Remember, we moved helium. So now this is the only tricky part about Lewis symbols. The first 2 dots always go together. So remember how we said we can have 2 electrons on that innermost shell? That's why. So we draw it out here with the 2 electrons next to each other. So helium has 2 dots. Boom, boom, just like that. Let's go to the next one, beryllium. So we have beryllium here. Beryllium also has 2 dots, 1 and 2. 2 valence electrons, you always draw the first together. And we could keep going. Magnesium has 2, 1 and 2. So let's keep going to boron. Boron has 3 valence electrons. Remember, the first 2 always go together. 1, 2. For the third one, you can put it anywhere you want. It could go here, it could go here, or it could go here. It doesn't matter where you go, but you just have to be consistent. Oh, you need to erase. And you can only have 3 total. So we have 2 together and then 3 on the outside. We would do the same thing for aluminum, and then so on and so forth, okay? Now let's go to carbon. Carbon has 4 valence electrons. So 1, 2 go together. The rest, it doesn't matter. 3 and 4. I could have put 1 up here in this spot. It doesn't matter. We just want to be consistent and only have 4 total. And so now we have nitrogen. Nitrogen has 5 valence electrons. So 1, 2, and then 3, 4, 5. Again, it doesn't matter where you put them, it just matters that the first 2 go together. So now for oxygen, I could start down here, 1, 2, then you just go around, 3, 4, 5. I have 1 more valence electron, so you just have to double up. It doesn't matter where, just pick one and double up. Then fluorine, that is 7. So 1, 2, 3, 4, 5, 6, and 7. Okay, for neon, our first noble gas, we have neon here. We go 1, 2, and then 3, 4, 5, 6, 7, and 8. Okay, so it has 8 electrons. They're all together. As long as you keep the first 2 together, that's all that matters. All right, so now I'm going to draw out some for silicon, and I want you to try to decide which is the correct answer. So for silicon, we know it has 4 valence electrons. It's positioned right underneath carbon. Here it is, so 4 valence electrons. So let's draw out 3 different structures. You're either going to answer multiple choice answer A for this, so it's going to look like this one. Answer B is if you think silicon looks like this. And answer C is if you think silicon looks like this one. Good luck. All right, did you get an answer? Hopefully you picked answer C because that is absolutely correct. In order to do this, all you had to do is draw the first 2 electrons together, 1, 2, and then 3, 4. It doesn't matter where you put them. This would have also been a correct answer. So the last thing I want to do is introduce one more piece of information, which is called a lone pair of electrons. Now, some people will just refer to it as a lone pair. Some people write it out as just LP, but all of it means the same thing. It is just saying that you have 2 electrons on some kind of symbol. So here's your thing. Here's silicon, 2 electrons that are together. They're a pair of electrons, so they're sitting like this. If I were to draw out an energy level, I would have 1 electron here, 1 electron here. I don't expect you to know what this means, but just know that those first 2 electrons go together. Remember, here's your nucleus, here's your inner shell, here's 1, here's 2. So it's just 2 electrons that are together, paired up in an energy level, and so that's why we put these together like this, right? We put the first 2 together. This is considered a lone pair of electrons. Anytime you have 2 electrons together, if this was a correct symbol over here, which it is not, this technically has 1, 2 lone pairs of electrons. So that's how you count a pair. So I want to ask you a quick question. How many lone pairs do you think sulfur has? Okay, we're just looking for the number of lone pairs. Go. All right, did we get an answer? Hopefully you did. So the first thing you had to do was go to your periodic table and find sulfur. So we're going to go all the way up to the top, and sulfur sits right underneath oxygen. And so it has 6 valence electrons. So we'll go all the way down here. So it has 6 valence electrons. We had to draw that out. First 2 to go together. 1, 2, 3, 4, 5, and 6. And so now all we're doing is looking for 2 electrons that are grouped together. So here's 1 lone pair, and here's 2 lone pairs. So hopefully you put the answer 2, because that is correct. Take care of yourself, drink water, and have a great day.